Hello. Now we will do the parallel axis theorem. First thing is why we need to do this theorem. The thing is, till now we have come across so many moment of inertia. We have calculated so many moment of inertia about so many axes for so many bodies. So we have a formula for moment of inertia of a point mass about an axis. We have a formula for rod about an axis which is passing through its center of mass and perpendicular to rod. We have a formula for moment of inertia of a rod about an axis which is perpendicular and passing through the corner. We have moment of inertia for circular ring, for circular disc about their diameters. And we have moment of inertia for hollow sphere and the solid sphere about their respective diameters. The thing is, when we talk about moment of inertia, it depends upon two things. One is a body, and second is the axis about which we are calculating the moment of inertia. Now, once we choose the body, let's say we have chosen the solid sphere. So once we choose the axis, once we choose the body, our body is fixed. But corresponding to a single body, there are infinite possible ways to select the axis. There are infinite possible axes. And as you remember, when we calculated the moment of inertia for a rod about the axis which is passing through the center of mass and the axis which was passing through the corner, the moment of inertia was different. So same thing will be happening for the solid body also, solid sphere also. So we have a formula for solid sphere about the axis which is passing through the diameter. But if we want to calculate the moment of inertia about any other axis, do we need to calculate one more time that thing, or do we have some easier method? Because you see, if every time we have to calculate the moment of inertia for a given body about the given axis, every time it will be a question of calculating the moment of inertia. We cannot use this moment of inertia for some further questions. So we need some easy method. And we cannot memorize infinite number of formulas also, corresponding to each and every axis. So what we do, corresponding to the different bodies, about some specific axes, we calculate moment of inertia and we memorize them. So we have moment of inertia for point mass, about our axis, for rod also, about one or two axes, for ring also we know moment of inertia about one axis, for disc also we memorize, for cylinder also we memorize, for hollow sphere and the solid sphere also we memorize, corresponding to one axis each. And then after, we devise some method to further calculate the moment of inertia for the same body, but about different axes. If we remember the moment of inertia for that same body about one axis, from that axis we can have the moment of inertia about different axes. So to do that, what we do, we devise two theorems. And out of those two theorems, one is parallel axis theorem. So in this theorem, we will learn how to make the relationship for the same body, moment of inertia of the same body about two axes. So if I'll be making the formula for moment of inertia about this axis and this axis. And if any of the moment of inertia is known to us, if I remember the moment of inertia about this axis, and if I remember the formula, then using the formula and using the moment of inertia about this axis, I'll be calculating the moment of inertia about this axis and any other axis possible. You see. So other theorem will be the perpendicular axis theorem that we will learn in the next lecture. So in this lecture, we will be making the relationship between the moment of inertia for same body about two axes which are parallel to each other. That's the condition. Okay. So if we want to use this theorem, there are two specific conditions to use this theorem. The first condition to use this theorem is these two axes, the two axes which we are taking here, these two axes has to be parallel. The axis we are taking, they has to be parallel axis. Has to be parallel axis. So whatever relationship we are going to make, that relationship is only valid when the axis is going to be parallel. Okay. This theorem is applicable for any kind of body, whether it is a planar body or a 3D body, any body, or even for a linear body. Whatever kind of body it is, this theorem is applicable. This parallel axis theorem is applicable for any kind of body. One condition, the axis we are taking, they have to be parallel. And the second condition is, out of these two axes, one axis has to pass through the center of mass. Meaning this axis, I'm assuming this is passing through the center of mass. Meaning along the way of this axis, there is a center of mass somewhere. Let's say here is the center of mass. So the moment of inertia about this axis, I'll start calling it as ICM. And you can see there are infinite number of possible axes which will be passing through the center of mass. Any number of axes will be passing through the center of mass. But so basically we'll be getting the set of relationship, meaning all the axes which are parallel, and if one of the axes is passing through center of mass, then will be this relationship will be valid everywhere then. So the first condition is the axis has to be parallel. The axes which we are taking here, they have to be parallel. And second is one axis should pass through center of mass. These are two conditions. Other than these two conditions, there is no third condition is there. Okay. So if I'm having any body and if there are two axes, one of the axes is passing through the center of mass, in that case I can make the relationship, we can make the relationship between the moment of inertia of this body about these two axes. Okay. So let's see how to make it. So this is my body. It can be 2D, it can be 3D. And in this body, obviously this is a random body, so we have to cut the element. This is the element we have cut. This is the point element we have cut. And the mass of this element I'm taking as dm. Okay, this is one axis which is passing through the center of mass, and this is another axis which is parallel to the first one. The distance between these two axes is d I'm taking. Okay, the total mass of this body I'm defining as capital M. Capital M is the total mass of the body. Okay, so the distance of the point element, with respect to axis, perpendicular distance, I'm defining as RCM. Okay, so if the RCM is the distance of the element with respect to this axis, I'm calling it 1 for a time being and this as 2. So with respect to 1, if the distance is RCM, then with respect to 2, this distance will become RCM plus D. Because see, it is a little bit further. Okay, so let's write the formula for moment of inertia. So if I have to define the moment of inertia, here I'm defining as I, there I'm calling it ICM. So moment of inertia ICM, if I want to define, the moment of inertia ICM will be equals to integration of moment of inertia of the element. So we calculate the moment of inertia for element and then we integrate it, assuming whole body should be covered. And my element is a point element, and we know the moment of inertia, formula for moment of inertia for point element. For point element, the formula is R square dm. In place of R, we have to write RCM dm. So this is the moment of inertia for point element, and if we integrate it corresponding to whole body, we'll be getting the moment of inertia for the whole body about this given axis. About the axis, we have calculated the RCM. So this becomes the moment of inertia for the whole body about the axis passing through the center of mass. Let's call it equation 1. Now, if you make the formula for moment of inertia, again for the same body but about this axis, then let's call it I. It will be equals to integration of distance of the element. It's the same element I'm taking this time also, which is RCM plus of D, distance square multiplied with mass dm. Because my element is a point element, and for the point element, moment of inertia is R square dm, where R is the distance of the element with respect to the axis, and the dm is the mass of the element. Okay, now let's start with this one. So let's open it. So I will be equals to, let's open it. If I open this, it will be RCM square plus D square plus 2 times of D multiplied with RCM dm. So let's separate this. It will be integration of RCM square dm plus d square integration of dm, because see this d square, d is a constant. It's the distance between these two axes. So it does not depend upon the element, so we can take it out of the integration sign. Plus here also 2d integration of RCM dm. Okay. So this becomes the moment of inertia for the whole body about this axis, which is not passing through the center of mass. Now you see this. This is R square Cm dm. This is nothing but the moment of inertia for the same body about the axis which is passing through the center of mass from this formula, or from this formula. You can replace this value. So I will be equals to ICM plus d square integration of dm. So if you integrate the dm, if you integrate the mass corresponding to the whole body, you'll be getting the total mass of the body multiplied with capital M, which is the mass of the whole body, plus 2d integration of RCM dm. That becomes ICM plus md square plus, now you see this thing. So I'm going to do something here. So I'll be writing it 2D, integration of RCM dm, and I'll be dividing it by integration dm, and I'll be multiplying it by integration dm. So I have divided and multiplied by the same quantity. So there is no change we have done. So if you see here, it is ICM plus MD square plus, now you see this quantity. It is integration of RDM divided by integration of dm. This is the formula. If you remember, we used to have the formula for defining the center of mass. The center of mass formula used to be defined as RDM divided by dm. And if you can see, when we used to define the center of mass, the origin for this RCM and the origin for this R has to be same. So whatever used to be the origin for the R, the same used to be the origin for RCM. So this formula represents the RCM. And this is the same formula we are getting here. So this whole quantity will be converted into RCM. But the thing is, when it converts into the RCM, the origin, whatever origin we were taking here, the same origin will be converted here also. And if you can see, here it is R, here it is RCM. So RCM is the distance. RCM is the distance of the element calculated with respect to the center of mass. So while we were calculating the RCM, the origin was at the center of mass itself. When we were calculating the RCM, for this RCM, this is the origin. And this origin is at the center of mass. So when we will be getting the center of mass, we'll be getting about the same origin. And that origin at the origin itself. Okay. So we'll be getting the center of mass coordinate, we'll be getting the position vector of center of mass with respect to center of mass itself. And position vector of anything with respect to itself is going to be the 0. So this whole value will convert into 0. And because of that, this I will be equals to ICM plus MD square. That becomes the formula. So this is your parallel axis theorem. In this theorem, if you can see, we get the relationship between the two moment of inertia. One, which is I, and second, which is ICM. This ICM is the moment of inertia for the body about the axis, which is passing through the center of mass, and I is the moment of inertia of the same body about the axis which is not passing through the center of mass, but which is parallel to this ICM. Okay, so this is the relationship we are getting. And if you see this formula, in this formula, this is moment of inertia we are talking about, which cannot be negative quantity. So ICM is going to be the positive quantity, M is going to be the positive quantity, and D square is going to be the positive quantity. So right hand side, if you see, there are two things, and both are going to be the positive quantities. Okay, so you can see this thing. If for a time being, I assume this D is a variable, meaning I want to check if I move this axis is fixed. If I move this axis, for what location, for what value of D, I'll be getting the least moment of inertia. If I'm interested in that, so to make this value I least, you have to make this whole value 0. So when D will be 0, this I will be equals to ICM, and at that time I will be having the least value. So based upon that, we can say, when we talk about the moment of inertia, among a set of parallel axes, so if I'm having a set of parallel axes, all parallel axes, then moment of inertia for a given body will be least about the axis, among these axes, which is passing through the center of mass. Now you see, when I'm talking about the set of parallel axes, I'm saying all the axes which I'm comparing right now, they all are parallel. I'm not comparing between these axes which are not parallel. Okay, so it's always about the parallel axes. So if you choose one direction for axis, then in that direction, whatever axes are possible, any number of axes are possible in that direction. So out of those number of axes which are possible in this direction, the axis which will be passing through the center of mass, about that axis, that body will be having the least moment of inertia. That thing you can memorize. So the body is going to have the, meaning if it is a set of parallel axes, for a set of parallel axes, moment of inertia is least for the axis which is passing through center of mass. Okay, this kind of become a second theorem based upon this. So this is a relationship you have to memorize. I is equals to ICM plus MD square. So this formula, meaning if you out of these two axes, if out of these two moment of inertia, if you know any one of the moment of inertia, then you can calculate the other moment of inertia. Okay, so if you have the moment of inertia about any axis, then in that direction, any axis, if you want to calculate the moment of inertia, you will be able to calculate. But you have to memorize that when you want to use this formula is valid between two moment of inertia, between moment of inertia about the two axes for the same body. But out of those two axes, one axis has to be the passing through the center of mass if you want to use the formula. So basically, if I'm having these two axes, this one, I'm calling it 2 and this is 3. I cannot directly use the formula between these two axes. I cannot use it. If I want to use the formula between these two axes, what I'll do, I'll make the formula between these two and I'll make the formula between these two. And then by subtracting or adding, we'll be getting the formula between these two axes. Not directly, but indirectly we can get the formula. Okay, so these are the things you can memorize out of this parallel axis theorem. One is this formula you have to memorize. Then these two conditions are there. They are very important conditions because many a time examiner plays with a condition. Okay, this condition you should memorize, and this is the relationship. Meaning if there is an axis passing through the center of mass, you can outrightly say in that direction, any axis which is possible in that direction, the axis which is passing through the center of mass is going to have the least moment of inertia. Okay, so thank you.